for the recent LIGO discovery. Hanna, professor in physics. Is the co-chair of, what's that? Compact binary coalescence group, right? So he'll talk everything about LIGO discovery. Please.
So first things first, can everyone hear me without a microphone? I will put on the microphone if you want it. Okay, we're going to go this way. All right, so thank you for inviting me. It's a pleasure to be here. I realize that even though physics and astronomy buildings are adjacent, I don't hardly ever get to come and see my astronomy colleagues, so it's good to be here. The second thing I want to confess is that this talk was a total bait and switch. So when Donghui asked me to give this colloquium, I had already had some privileged information about what LIGO may or may not have seen. And so I gave this wonderfully boring title as what I said we were going to be talking about today. And it was going to be this normal LIGO talk, right, where I stand up here and say, here's what we've been trying to do for 10 years. It's really hard. Maybe we'll find some stuff. And it was going to be a complete snorefest. But I decided to go ahead and change the talk title today to Gravitational Waves Discovered. Hopefully my laser pointer will heat up during this time. Okay, so, and that's it. And so, in principle, this is on behalf of the LIGO and Virgo collaborations. I should have had this talk reviewed, don't tell them. But anyway, so let's get started. Maybe. Okay, so probably most of you had heard about last week's somewhat landmark announcement from the LIGO and Virgo collaborations that gravitational waves had been discovered. And so what we said was that a little over 1 billion years ago, there was a binary black hole system, stellar mass, but pretty heavy for stellar mass, that had potentially been orbiting for billions of years. And it, during that time, had been sort of slowly giving off energy due to gravitational wave emission. And that was causing its orbit to shrink. And in the last few tenths of a second, it was orbiting at a frequency high enough to produce gravitational waves detectable here on Earth by advanced LIGO. So this is, I'm going to lower the lights. So this is an actual numerical simulation of this of a system consistent with what we observed. And you can see that the binary was orbiting and eventually merged together and formed a single black hole that then settled down to a stationary spacetime. So this talk is pretty much mostly going to be about the discovery. I will, of course, spend a little bit of time giving some background and other things, and then at the end, maybe give you a bit of an inkling of what we should expect in the future. So before we get ahead of ourselves, I don't know why none of my devices are working. Before we get too ahead of ourselves, so I think we should probably start with what are gravitational waves. So gravitational waves are a prediction from Einstein's theory of general relativity. And so general relativity is our modern perspective on gravity. And the idea is that very dense, massive objects actually warp and curve space-time, and that our sort of motion through that curved space-time is what we understand as gravity. And we often think about gravity in sort of static situations. I mean, yeah, the Earth's moving through the solar system and things like that, but for the most part, we just, our experience is that this gravitational pull towards the center of the Earth, and that's that. There are, of course, really extreme objects in the universe, like neutron stars and black holes that are extremely dense. They pack, neutron stars pack more than the mass of our sun into, 10 kilometer, order 10 kilometer diameter. And these objects themselves can really warp space-time extremely. So they really cause a significant curvature. They have a very strong gravity. And what's even more impressive is that these systems can be in binary systems. And because they're so compact, they can get very close together and still have sort of stable circular orbits. So in this artist's rendition of gravitational waves, which I think has seen a lot of popular media lately, you can see these two neutron stars, which are extremely compact objects, warping space-time here as sort of a single two-dimensional sheet through space. And the idea is that these things are warping space-time obviously quite dynamically. And so this dynamic changing in space-time, in part, it can propagate away to infinity and have observable consequences. And these are what we call gravitational waves. So even before LIGO made the announcement of the discovery of gravitational waves, we actually had already more or less confirmed their existence. And the way we had done that actually was folks starting in the early 70s had made very precise measurements of binary pulsar systems. So these are systems of two neutron stars in a fairly tight orbit, but not anywhere near as tight as what we observed with the binary black hole. And what was observed was that the orbital period was changing as a function of time. It was decreasing. So the system was slowly getting closer together. And this is not quite that. This is a cumulative periastron shift. But this plot shows a prediction in the solid line from general relativity for what you would expect if the system is losing energy due to gravitational wave emission. And the red dots are there we go. The red dots are the actual observed data points. So even though this wasn't direct evidence, we didn't actually measure the effect on space itself by gravitational waves. We saw that the energy loss in the system was basically in agreement with what we would expect. And I have to say that this was extremely compelling evidence. If it weren't, of course, for the measurement of the system and really believing that gravitational waves were something we could detect, I don't think the present effort would have ever been funded. So this is a really monumental thing to have had detected at this point in history. But what we're after is something a little bit different. So we want to actually measure the effect of the gravitational wave being emitted from some distant system here on Earth. And so to do that, we want to figure out, obviously, what the effect is for an observer here. So here, if you imagine a gravitational wave propagating into this screen, then the effect is that it will stretch and squeeze space in a direction transverse to the propagation. So if the gravitational wave is propagating exactly normal to this screen, then it will stretch and squeeze space in different directions as it passes through. And the stretching and squeezing, the relative change in the length of this grid divided by the length is the strain, and that's actually how we characterize the overall amplitude of the effect of gravitational waves. So obviously we see in this extreme example that the change in length in this grid is almost as big as the length itself. It's sort of an ordered unity strain. The strains that we recently detected with LIGO were 1 part in 10 to the 21, which is a very small number. More on that later. It's actually, believe it or not, bigger than we thought we would ever detect, so there's good news there. Anyway, so this strain is what we're after, and the way we would basically observe a gravitational wave strain is if we could put points at distant places on this grid, we would be able to actually measure a change in the relative distance between the points. And so the basic idea of gravitational wave detection is to very carefully measure distances between points. And so to do that, the modern technology, this is something, by the way, that people have been working on really for decades. It started with different technologies than this, but beginning as early as the 70s, very serious designs were put forward to use laser interferometers for gravitational wave detection. And the basic idea is actually pretty straightforward. We have a laser that goes to a beam splitter. The beam splitter causes half of the light to be reflected at some 90-degree angle. The rest of it passes straight through. It goes down 2 orthogonal arms. Let's ignore this part for a second. I'll explain that in the next slide. It goes down 2 orthogonal arms, and there's a mirror that causes the light to then bounce back into the beam splitter, and then is detected on a photodetector after it recombines from both arms. If the arm lengths were actually the same, then when the light recombines here, we would get constructive interference. If, however, a gravitational wave were passing in this screen, and this were our interferometer, and here, this is now a ring of particles, but you can think of this as, the same sort of grid here. If a gravitational wave is passing through the screen, obviously it's going to be a time-dependent change in the length of the arms of this interferometer, and we're going to be able to read that out by how the laser light recombines and interferes. I should also add that this sort of characteristic oscillation would be consistent with a fairly low frequency compact binary merger that's really just sort of beginning to be detectable for LIGO. Yes?
So if a really massive gravitational wave passes through this room, would we see the room physically deform? I guess the question is the interferometer itself, like the physical structure deforming, or is the path length along the arms?
The path length, so the interferometer itself is actually in vacuum, and so that the end mirrors are basically acting as test masses in vacuum that can actually sort of be used to determine the distance, from the passing gravitational wave. There would be like some rigidity to a mechanical system to gravitational waves, like there would actually be a force that in principle a mechanical system could prevent them being crushed by the gravitation.
The gravity wave would try and deform this.
It would actually, and so the original devices, the resonant bar devices, actually had sort of they actually had a transducer. So it's basically excited a phonon, it excited an acoustic mode in a large metal bar. Is how they originally worked. Good question. Okay, so the sort of toy model on the previous slide is really in effect what we've built. Now the scale is pretty big. So LIGO operates 2 different detectors, one in Washington State, one in Louisiana. They are almost exactly 3,000 kilometers apart. The light travel time between the 2 is 10 milliseconds. We expect gravitational waves to travel at the speed of light, so the gravitational wave travel time between the 2 sites is also 10 milliseconds. So the optical layout for LIGO is not so different than a regular interferometer, which would have just simple mirrors at the end of each arm. But one of the important differences is these additional mirrors inside here labeled as test masses. But these are actually mirrors that set up a resonant cavity, a partially resonant cavity in each arm. And there's a lot of different ways you can think of how this affects the measurement process, but the one that's sort of most apparent from this graph is if we send 20 watts of laser light into the system, then with this resonant cavity, which allows the light to effectively sort of bounce back and forth many times before leaking back into the beam splitter, we're actually able to accumulate 100 kilowatts of, circulating laser power. And it gives us sort of a lot of extra photons in this cavity to interact with the change in path length and allow us to actually measure the gravitational wave more effectively. So to give a sense of how well we do with one of these instruments, you probably, some of you who've seen LIGO talks, have seen plots like this before. And they're the plots that we all show because we feel compelled to, I think. And everyone hates or doesn't understand or something, but I'm going to show you the plot anyway. It's in the PRL, so that ship is sailed. This plot gives the characteristic level of the strain noise on the y-axis. So this is units of strain per root hertz. It's a function of frequency. So on the x-axis we have frequency in hertz. And you can see the numbers here, hopefully, for even people in the back of the room. 10 to the minus 23, 10 to the minus 22, 10 to the minus 21. So what this is telling you is the characteristic level of the strain noise as a function of frequency in the LIGO detector. And why we want to know what the noise is because if we want to observe signals, obviously, we need the signal to stand out above the noise. So wherever this curve is lowest is where we're most sensitive to gravitational waves. So LIGO is most sensitive to gravitational waves that have frequencies of oscillation sort of around 100 hertz. And you can see how sensitive we actually are. If you were to integrate this over some small bandwidth, we really would be able to measure strains at sort of parts in 10 to the 23. Now, we often, and so you've probably heard, if you've again heard LIGO talks, or if you've read some of the popular stuff that's been around, you'll know that there's this strong analogy with gravitational waves being more like sound. And of course, the fact that they are sort of shaking up space-time and vibrating is a great analogy for sound. And we do use it in the community. We talk about gravitational wave sources being loud rather than bright. And the coincidence, well, the analogy is even quite more interesting for LIGO's case, because not only is there an analogy to sound, but it turns out that if you look at this, the frequencies that LIGO is actually most sensitive to are in fact the frequencies that the human ear is roughly most sensitive to. And you can put the human ear response, not to scale, on top of the LIGO thing. And okay, it's not perfect, but the truth of the matter is that we're actually listening to gravitational waves and the frequencies that the ears can hear. So we'll get a demo of that later on. I don't know that it's true anymore, but in initial LIGO, when I was a grad student doing shifts there, we actually had this thing hooked up to a loudspeaker. So you could go into the room and just listen to LIGO, just play it. And what's that?
Jody Foster.
Yeah, exactly. And in fact, I more than once made the somewhat cynical joke that we should just pay graduate students to have headphones and screw this whole supercomputer stuff. Because, computers are a huge pain. So anyway, it still certainly is true, but I'm not sure that anyone has the speakers turned on these days, which is kind of sad. Okay, so then what did we hear? On September 14th, 2015, so last fall, we heard basically a nearly identical sound, saw an identical waveform at both LIGO sites. The waveform, the signal arrived 7 milliseconds apart, which is completely consistent with a finite propagation speed from gravitational waves. This plot has so much information, so we'll spend a little bit of time here. The top row, strain, in units of 10 to the minus 21, so this is 1 times 10 to the minus 21. That's changing the length. I forgot to give you my standard analogy. We were sort of looking at parts in 10 to the 23, which is what we thought we would detect things at. That's equivalent to the width of your thumb compared to the width of the Milky Way galaxy. This was whopping loud. This is almost the same as the height of a person compared to the Milky Way galaxy. So, way bigger than we thought. Here you see the almost unadulterated strain signal. So this is really like the raw data that's come out of LIGO. The only thing that's been done to it is it's been bandpass filtered. So we've only allowed frequencies sort of in the most sensitive region to be displayed here. Otherwise, it would be dominated by low frequency, like seismic motion and things. But really, this is very close to the raw data. And hopefully, your eye, is drawn towards the very, similar features of the two waveforms observed in Stanford and Livingston. The reconstructed waveform, which you can think of as sort of a denoised waveform, I'm trying to pull the noise out of it, done in a couple of different ways. One that's highly model dependent, the other that's not very model dependent, actually agrees very well. And you can see this is sort of the denoised waveform that was expected to be found. And here, in this third row, is the residual. If you subtract the sort of best fit waveform from the data, what you're left over with is quite consistent with noise.
So
now, yes?
How do you do the timing synchronization between the two sites, and given that time difference, how well can you constrain the origin on the sky of the source?
Both good questions. The synchronization, there's a couple of different things involved. It actually uses GPS, which by most standards is pretty crappy, but we have 100 microsecond timing resolution, which is enough for what we're trying to do. These are very low frequency things, right? So you're talking about things that are oscillating at tens of hertz and hundreds of hertz. So the timing resolution you need is the timing resolution is is really limited by the physics. So if you think of a lambda over d, our lambda, like our d is pretty big between the two sites, 3,000 kilometers, but our lambda is like almost as big in most cases. So it's, and actually at low frequencies even bigger. So our ability to localize things in the sky is not that good. Yes?
Are the residuals that we're seeing there white noise, Gaussian, or
No.
monochrome?
They're autocorrelated. And that you would, it's a really interesting question. You wouldn't believe how long we debated about this. If you want to talk to me after this, I certainly would. From a data analyst perspective, we would have liked to have seen this whitened with the autocorrelation removed. The instrument folks wanted to plot something as close to the raw data as possible. So this has been band passed, but has a basically what you're seeing is.
Have you included an autoregressive component in your model?
Yes. That model includes the factor of the spectrum.
Okay.
Yes, good question. Well. So again, this was really whopping loud. So the signal to noise ratio in Hanford was 20 and Livingston was 13. We would have been pretty thrilled if it would have been half that much. I'd have probably still been standing up here in front of you today. Might have taken a little bit longer, but we would have pretty much been thrilled if it was half as much. The other thing that, so I want to say that we learned about this pretty much straight away. This was detected by what we call colloquially a burst search. It's an unmodeled, no, that's not the right terminology. It's a search that makes minimum assumptions about the sort of signals that it's trying to detect, other than that they have to look similar in both detectors within the physical constraints. So it's looking for things that we don't model all that well, like supernovas and other things, but happen to be sensitive to this signal. And we knew within like a few minutes that this had come through. And basically upon seeing the waveform, and specifically this fourth row, which is the frequency as a function of time, so this is a time frequency plot, seeing that this signal seems to have power, so this is sort of it's an indication of how much amplitude is in each tile. It has power that goes from low frequency and evolves quickly upward, chirps upward to high frequency, and looks very similar in both detectors. This is the exact prediction from general relativity for a binary merger. So as soon as we saw this, even without doing any fancy statistics, we more or less convinced ourselves what we'd seen.
Can you explain the 50% difference in signal to noise?
Between LHO and LLO?
Yeah.
So at the time, the instruments were not exactly the same sensitivity, and they don't measure exactly the same projection, because they're misaligned a little bit. So they measure different polarization, and they see a little bit different of a response. Good question. So this smelled basically straight away like a binary black hole merger. All right, so we knew within minutes and probably then within hours what we were dealing with, but it took us several months afterwards to actually do everything carefully, vet the analysis, try to estimate the significance of this thing so we could decide whether or not we really were going to announce a discovery. And we had a lot of tools to throw at this. We've obviously been preparing for a long time, and sort of we're happy to finally have something of interest to try all this stuff out on. We had two completely independently implemented matched filter analyses. I'm not going to go into too much technical detail there, but the idea is with binary systems, I'll explain later, we really have a good idea of what they should look like and can actually predict the waveforms very accurately. So the sort of best detection technique is to actually just try to literally match a bunch of different waveforms with the data and see which one fits the best. And so that's effectively what's being done here. Now we had two entirely independently implemented analyses that really treat how they process the data pretty differently, how they estimate the background, how they do the statistics was all really quite different between the two. But both effectively ranked this event as completely off the charts. So the end, what we quote is greater than 5.1 sigma, and I'll try to convince you that that's really that it's really much more significant than that. So here you have the results of two completely independent analyses. They're not independent in the sense they look at the same data, obviously, but two different takes of this that we tried to put sort of in a similar plot. I could spend forever talking about what this plot really means, but let me try to make it as brief as possible. On the y-axis in both plots, we have number of events. This sort of gives you the sort of expected number of events if what you've measured is noise.
What's the unit of time?
So the unit of time we've measured, so this analysis comes from 38 or 39 days of coincident data. Or sorry, of calendar data. So there was about 16 days where the detectors were both operating. So this is to be interpreted as number of events in the 16-day coincident period. Great question. So the black and blue lines represent our expected background with a couple of different ways of estimating it. I probably don't have time to go into the subtleties of it. And the orange squares are the actual observed result. So you can see that for the most part, for high event counts, in both cases, the orange lies directly on top of the expected background from noise, but there is this point way out here on both plots. The x-axis, by the way, sorry, I got distracted. The x-axis is different for both plots. That's the one thing that had to be different. This actually reflects the way the analysis is done. Both mean what we call a ranking statistic or a detection statistic. Bigger numbers are supposed to indicate more likely to be a gravitational wave. But other than that, the thing that's important isn't actually the numerical value of this particular quantity necessarily, but where the observation lies with respect to the background. So in both cases, here and here, we have one event, which is GW150914, sits out extremely far to the right. These numbers being big indicates that it's more likely to be a gravitational wave, but then when you look at the expected background, in both cases, there's just simply nothing there. The plot cuts off at 10 to the minus 8 expected events, which is roughly then equivalent to a 10 to the minus 8 false alarm probability. And you know, we can't really do a reliable estimate for getting something out here, and I should also add that this background estimate is absurdly conservative, and I probably don't have time to talk about it too much. But either way, if you sort of imagined continuing lines, it's pretty clear that this is really quite off the charts.
So what are the couple of points you had on a couple of sigmas just off the background curve?
That's an excellent question addressed in a later slide. Now you all pay attention, right? Okay, so before we get, so the fact that we observed something is great. So now what did we learn about the system? For very good reasons, for very good reasons, a binary black hole merge is basically described in 3 different phases. It's of course this continuous process. The gravitational waves cause the orbit to shrink and things gets closer and closer and closer together and eventually merges. But we actually break it into 3 distinct phases. There's the in-spiral phase. This could potentially last billions of years. It could actually last much longer than the age of the universe. This is when the binary is sort of in a far separation and it's hardly radiating any energy in gravitational waves. There's nothing to really change its orbit. It's just going to orbit happily, look just like you would expect in sort of normal Newtonian mechanics. It may stay like this for a long, long time. But it will be losing energy, and at some point, the energy loss to gravitational waves will cause it to get closer. Now, it's a bit of a runaway reaction. So once you get the binary closer, the gravitational wave energy emitted actually goes up. So you lose more energy as it gets closer, which means it's getting closer. The orbital period is shrinking at an ever-increasing rate. So as it gets very close together, it's orbiting very quickly, it's emitting even more energy, and in the final moments, it's driven to merge together. At some point, there's no longer sort of any normal, stable, circular orbits, and the 2 objects merge together. We call this the merger phase. This used to be thought of as this crazy process that, who knows what's happened. Numerical relativity has actually taught us that it's actually not that crazy. It's pretty normal looking. Oh well. Highly nonlinear, obviously. You're probing really, you need the full solutions to the GR equations to get this. And then in the end, if it's a black hole, it merges and forms another single black hole, and it sort of radiates its last bit of gravitational waves and settles down to a stationary spacetime. We normally describe this binary evolution with, well, it can be more than this, with 15 parameters. Actually, the intrinsic parameters to the system are only 8. The rest of them are extrinsic. What I mean by that is our observation of the gravitational waves depends on sort of our orientation and location with respect to the source. So you probably can guess what they are. So black holes are pretty simple objects. Black holes are really just defined by masses and spins. If you have 2 of them, you have 2 masses and 2 spins. So the first set of parameters, component masses, m1 and m2. That accounts for 2 of our parameters. The spins, of course, are vector quantities. The orientations with respect to each other certainly matter in the dynamics. You have 6 components, 3 components for the spin of the first object, 3 components for the spin of the second object. We often talk about the spin magnitude of each object in a dimensionless way. If you've looked at the papers, you will have seen A, which is a dimensionless spin normalized to the maximum spin a black hole can have. So this is always less than or equal to 1. The rest of the parameters are extrinsic parameters. So there's the binary location, which is just really the coordinates, right ascension, declination, distance to the binary. The orientation and have things having to do with polarization. This is supposed to be a psi. 3 coordinates there. And of course, the coalescence time, which just determines when the binary actually merges together. So all in all, in 15 parameters, those of you thinking about this might have realized there's no eccentricity quoted here. The eccentricity of the orbit is assumed to be basically 0. It was checked, it is basically 0. Gravitational radiation circularizes orbits. So unless you have a pretty strange scenario, we're not expected to observe it. So all of these parameters, and really the intrinsic ones being...
You had a question?
Oh, sorry, yes, please.
Are you sensitive to polarization?
Yeah, but with LIGO, so each one only measures one of the gravitational wave polarizations. We would need another arm to get the rest. And the LIGO detectors actually are not that misaligned with respect to one another, so they kind of probe both polarizations, but not all that well. It was actually intentional. When we add Virgo into the mix, we really get the second polarization down better. Okay, so these binary parameters actually influence the gravitational wave signal that we see here on Earth. So every merger sounds different. The binary parameters, the masses, the spins, really do encode themselves on the gravitational wave strain. So we can really see the difference in the waveforms if you look at them, and you can hear the difference in the waveforms if you listen to them. And on both of our detection techniques, the matched filtering, which I sort of mentioned briefly earlier, and all of our statistical inference tools really are trying to just match a bunch of different models where we vary the binary parameters, match those to the data, and then see what we learn about them, including, of course, uncertainties in our measurements. So maybe this is a generational thing. I don't have it, but I don't know what this says about me. Shazam is this app for your phone that will, if you hold it up to something, you can tell what song you're listening to. So this is very, kind of very similar technology, actually. So visually, we have this 1-1 solar mass binary merging. So this, in principle, this waveform, which is the strain as a function of time. Sorry, this plot is a little small for those in the back of the room. This is a 1 second to 3.5 seconds. This is when it merges. Time units are completely arbitrary. This, in principle, goes back billions of years, or maybe hundreds of millions of years. I've plotted it only from 60 hertz up, so just the last bit that LIGO can observe. What I want you to see is the dramatic difference with what we would observe under the same constraints between a 1-1 solar mass binary and a 20-20 solar mass binary. So it's pretty clear that the waveforms here are quite a bit different. And in fact, if you were to listen to these, for those of you who need a little bit of a wake up, there's your 1-1. Yes, that's what we were waiting for. And the heavier one's even less impressive. The cosmic burst or something, I'm sure that's got to be out there somewhere. But the point is that, okay, they might sound ridiculous, But the way they sound or the way they look if you plot them is really encoding something about the physics of the system. And so our job is to carefully look at these waveforms and figure out what it's telling us about the binary. All right, so sorry. We'll go through this table somewhat slowly. Those of you who saw, this table is not in the main paper. I thought I had the archive number on here. Oh, I did something. So we've done a pretty complete analysis of the binary parameters, trying to infer what's going on. This is what we've learned. So we used two different waveform models. And just for the maybe sort of more interested people about the technical aspects of this, we can't, ideally we would use numerical relativity simulations for everything, and we just, make 1 billion numerical relativity simulations, and that would all be perfect, and it would be a great world. We can't do that. Don't have enough computing power to do that. So there's a sort of hybrid approach between sort of quasi-analytic and perturbative methods that are matched to numerical relativity embedded. And these are two models that are very common, excellent models in the fields. We basically used both of them. These are their technical names, EOBNR and IMR phenom. Neither model is capable of actually capturing all of the 8 intrinsic parameters. So the thing about it is that we've really only started to scratch the surface, and actually there's been a ton of progress even in the last few years, but of being able to really get a handle on how the spins affect the binary evolution at late stages, with the exception of full numerical relativity. So there's still a lot to be done here, but I just wanted the disclaimer that this model uses only components of the spins that are aligned. So instead of having a 6-dimensional space, we have a 2-dimensional space for spins. This component, or this system, adds a 3rd dimension which tries to capture some effective phenomenological parameter that influences the effective spin misalignment. But neither one of them are doing the full spin space. So by far the most accurate parameter that we can tell from the binary is the Chert mass. That's this special combination of the component masses. M1, M2 here, big M is the total mass. This is an important parameter for us because it's actually the parameter that dominates the sort of frequency evolution of the binary during the in-spiral phase. So it really tells you sort of how long the in-spiral is. And that's therefore the reason why it's the best measured. So the Chert mass, even though it's kind of an esoteric thing, we measure quite well. It's about 28, but the error bars are small. In this table, we've given median estimates with these numbers to the side giving the 90% interval. So about 28 plus or minus 2, roughly speaking. The component masses are not nearly as well measured, 36 and 28. The error bars are still sort of completely consistent with an equal mass binary. The mass ratio Q is 0.8, but the error bars include all the way up to the mass ratio of 1. So this really was a fairly equal mass binary. The total mass of the system starts to tell one of the interesting stories here. So there's 2 ways you can think of the total mass. You can think of the total mass as being the sums of the 2 black hole masses, if the black holes were sort of separated far away at infinity. And of course, the other total mass that's relevant is whatever the mass of the final black hole is. Two black holes start, and a final one is formed. And I'm sorry, it's a much smaller screen than I expected to be available. So the total mass from the 2 black holes that coalesced was about 65 solar masses. But the final mass of the black hole was only 62. So the total mass before is not equal to the total mass after, and of course this isn't surprising, but it means that 3 times the mass of our sun was actually radiated in gravitational waves. So these are dark objects. I mean, they're not radiating. I guess the quantum gravity guys might make fun of me if they're not radiating appreciably in anything other than gravitational waves. So all of the energy that would come from the mass difference between sort of initial masses and the final masses the final mass rather, has been radiated in gravitational waves. So really a tremendous amount of energy. Yes?
So those masses, at least with uncertainties of 4 or 5 solar masses, how well do you know the difference? Is that independently determined?
You mean the mass ratio? Or is it something like that? Oh, the difference as
Between the initial mass and final mass.
So it is quoted not in this table. Not in this table. But if you look in the paper, it's 3 plus or minus 1. So all of these things are extremely correlated. These are very complex. Doing this analysis takes months on supercomputers for people that do this for a living, and they're all really correlated. It's sometimes difficult to get an intuition for how things turn out, but the difference is known to plus or minus 1. Good question. Yes.
If you don't see the LIGO, is it more difficult to determine the final spin?
So that's another good and somewhat controversial question. You can actually try to analyze these by the 3 phases separately, but in actual fact, this comes from a numerical model that specifies the entire evolution. So the ring down part of it's kind of coming along for free, like calibrated to numerical relativity. So basically, the initial state implies the final state with no ambiguity.
If the signal too long, it gets worse, and then I think more difficult to see the LIGO.
Well, but that's the thing, is it's one of these, the model applies to all of the phases, right? So if you believe GR is right, and you believe you determined a black hole, or you found a black hole, then you can learn a lot about the final state even from the initial state, if you can measure those parameters well. I'm actually not going to talk too much about it today, but we did do some pretty reasonable tests to make sure that it is completely consistent with general relativity. So the spin magnitudes, again, this is very small, sorry about that. They're not well constrained at all. The dimensionless spin magnitudes can be anywhere between 0 and 1, and our analysis basically says they're somewhere between 0 and 1. So there you have it. Though this is a kind of misleading thing to say. I personally wouldn't, I would maybe, well, the folks that worked on this are all fantastic. I would have maybe emphasized this a little bit differently. Just because this is, this doesn't tell quite the right story. The thing that you really have to look at is this special combination of the spins, which we call an effective spin. We're not very good at naming things creatively. It's the sum of the 2 spins, the vector sum of the 2 spins projected onto the orbital angular momentum with some mass normalizations. It's measured much better. So if you can see the error bars here, it's measured much better, and it's consistent with 0. So it's not, you don't know if, so basically the scenario could be they're not spinning at the end. The component masses are not spinning that much. Or if they are spinning, they have to be anti-aligned with one another. So that's basically what this is saying. There's some projected along the orbital angular momentum has to be close to 0. If we had a sufficiently non-zero effective spin, another way of saying that is if the spins would be both large and aligned rather than anti-aligned, then there would have been a contribution to the final spin of the black hole from the angular momentum of the input black holes. So we know the final spin of the black hole pretty well, 0.67 plus minus 0.05. That we know very well. And that would have been different if the spins of the 2 objects would have been near maximal and aligned or anti-aligned. And so just looking at the spin magnitudes independently doesn't quite tell the right story. The truth is this is either pretty consistent with non-spinning, or we've somehow managed to get a scenario where it looks like this. I would vote on the first scenario where they're probably not spinning. The distance to this thing is not that well constrained either. 400 megaparsecs, but plus or minus 200. Sorry, we can't measure the redshift independently, so we just use a standard cosmology, and the redshift's about 0.09. So pretty nearby. Now, one of the things for those of you who, I don't know, for whatever reason may know something about these binary evolutions, if you have a spin component for the black holes that's actually in the plane of the orbital, in the orbital plane, so not something aligned with the orbital, not something aligned with the angular momentum, but actually in the plane, so you have spin directions components that are like this, then it actually causes the entire orbital plane to precess sort of like a top at late stages in the evolution. And in principle, this should actually cause detectable phase and amplitude modulation in what we observe, if it happens. To know, of course, what the components are everywhere, we really have to have the full 6-dimensional spin space covered, and that was actually not really ready to go at the time we published this paper. There are results from like bleeding edge models being run right now. I don't think anything's going to change. There's no clear indication of precession here. But on the other hand, it's also something you can't completely rule out because of how few cycles there are and other things. The one model that we use, this IMR phenom model, does use some phenomenological parameter chi p that's supposed to capture the sort of degree to which precession might be visible. It's in this histogram here, this is the posterior probability for this chi p parameter. The green, which is a little bit tricky to see, is the prior. The black and gray region is what was observed. Basically, it's completely consistent with what we put in. The prior for all of these things was that the spins were distributed isotropically. So there's not really much of a hint of precession here, but it's fun to imagine that might be that might be what's happening. Fear not. I hope it's not campus-wide, is it?
This happened earlier today.
Could we go back a couple slides to that
Yes.
same issue? Astrophysicists.
Oh, I think you came back.
Astrophysicists, one more please. Thank you. The issue of the anti-aligned spins. Astrophysicists studying repeating black holes in our galaxy and nearby galaxies. These are X-ray astronomers looking at the spectra of single accreting black holes, have concluded that in most cases, and there's quite a number known now, the black holes are rapidly spinning like 90%. So that doesn't answer the question of what your particular black hole binary components were doing, but it's pretty clear that most black holes that have an accretion process are spun up to 90%. And so to have two of them showing nothing, when you add them up, it's pretty weird.
Well,
given the astrophysicist thing.
yeah, so I mean, they certainly would have evolved, I guess, in a different environment, potentially. I was also a little surprised that there wasn't more of an indication for spin, frankly. It is what it is. I mean, the final black hole, of course, is spinning at 0.67, but that's entirely due to, I mean, not an accretion process. Well, I guess accretion in an extreme sense, accreting another black hole. So that's entirely due to all of the orbital angular momentum being absorbed in that black hole. So there you go, there's accretion.
So I guess
That dodged the question.
there was no accretion disk in the past history of these black holes.
I suppose at least not one that was able to spin this up enough. Unless somehow you had like, yeah. But I certainly agree that it does not seem consistent with very high spin and the same direction. Well, you know, sorry. The good news is that this was the only other video I had. So. Okay, now so this is something that I think a lot of people somehow missed. For a good reason, because we tried really hard not to make it such a big deal. If you look in the PRL, there was mention of the second loudest event, and it's not really played up that much in the paper for good reason. It's Stefan's question, in fact. But if you read all of the other companion papers in your spare time, of course, that we've published so far on this, it comes up a couple of times, so I want to spend a little bit of time on it. There was a second thing in the data set that was a little bit unusual. It doesn't nearly have the significance that we're going to stand up and say this is a gravitational wave detection. So we've had to give it some different name. As you might have gathered already, our GW and then UTC date is what we're going to now call all gravitational wave candidates. We didn't want to call this one that, so we called it LVT, but then the UTC date. And this LVT stands for LIGO Virgo Trigger. So something we're not willing to say is an event, but is something that's of interest. All right, enough about that. The false alarm probability is only 2 sigma, a little better than 2 sigma. So nothing at all to write home about. A couple of things though. One, remember how I said we had 2 entirely independent analyses, at least independently implemented analyses. In both analyses, the second loudest event was this same event. Now, we don't have a way of really quantifying this rigorously, but let me just say that as someone who worked on this now for a decade, it's pretty rare to have 2 completely independent analyses agree on noise. They tend to do a pretty good job of agreeing on things that aren't that noise-like, but agreeing on noise is pretty rare. The signal-to-noise ratio here is small, SNR 7 in each detector, so considerably smaller than GW150914. This is a really difficult to detect system. However, we've done some analysis assuming that it's real, just as a way of estimating its parameters and doing some other things. It is consistent with a binary black hole. Its chirp mass is lower than GW150914. It's only a 15 chirp mass instead of 28. It's at a further distance, 1100 megaparsecs, but with huge error bars. But it kind of smells right. All right, it's going to come up a little bit here before the talk's over. So some of the implications, well, it's just one event, so we can't, say tons and tons of stuff yet. But I think it's fair to say, and most of you in the room are experts on this, I think it's fair to say that as stellar mass black holes go, this one's a little heavy. The components were a bit on the heavy side, right? So, 30, 35 solar masses for each of the components. And if we think it's sort of a normal stellar evolution, it really means that we had to have progenitor stars that were pretty big. For that to happen, there have been a lot of plausible scenarios proposed in the past. It couldn't have shed much mass from some stellar wind part of its evolution, which probably means that it may be in a very low metallicity environment, less than half of the sun's metallicity. And this low metallicity environment you can think of as in 2 different ways. Either one, well, it was formed a really, really long time ago in the earlier universe and has just taken a long time to merge, or maybe there's some low metallicity environment that it was formed in. But nevertheless, it is a bit on the heavy side, so it's kind of interesting. And we'll have to see what the future holds there. Of course, one of the big questions on everyone's mind is, now that we've seen one of these things, what do we know about the rate? Like, well, I guess we've only had one, so our rate is still pretty uncertain. But it actually has helped. They're not that much. So the situation before GW150914 was the typical lousy, enormous error bars of anywhere between 0.1 and 300 mergers per gigaparsec cubed per year. Obviously, the 3 orders of magnitude uncertainty is what we've been up against for a long time. I am proud to say we have reduced it by an entire order of magnitude. We're now pretty sure there are at least 2 per gigaparsec year.
Is it for what mass ratio?
Well, so no, this is a great question. So this number is extremely uncertain. But no matter how you look at it, this small number is off the charts. And as you might imagine, off the table. As you might imagine, this is highly model dependent. So we did a full rates analysis. To calculate rates, we have to understand our sensitivity to gravitational waves. Since we have different ways of looking at gravitational wave data, we have to evaluate both and try to understand sensitivity. These are big supercomputer Monte Carlos. They take a long time. standard stuff. There are a couple of different ways we've looked at it. One is to consider GW150914 in its own class. So just pretend all black holes are that period, that type. If you do that, you get 16 or 17, but with pretty big error bars. We also took a look at LVT 15, 10, 12, and the rate implied there is a lot higher if it is a black hole. You can then imagine putting together a crazy distribution which is all black holes look like those two things, and that's what you would get. Of course, what most of you in the room would want to do would be to somehow have some sort of astrophysical distribution put in, and we did that a couple of different ways. Probably none of them are completely satisfying, but we constrained the masses of the black holes to be between 5 and 100 solar masses, and considered two different distributions, flat and log m. If you do that, you get around 30, and with some power law that emphasizes low mass. Yes, this is the initial mass function. Is that a good idea? No, but whatever. some power law that emphasizes low mass things as being more likely. And if you do that, not surprisingly, you would get a higher rate. So basically, like all of this and all of the uncertainty and whatever has been folded into this very, very, very conservative large range. But the only thing we've been able to say for sure is 0.1 is off the table. Okay, so going forward, here's the timeline. I am almost done, I promise. Here's the timeline for 01. 01 was 4 months. We had only published on 1/3 of the data. So the publications that have come out have only been 1/3 of 01's data. It's only been solar masses, only been up to 100 solar masses. We still have 2/3 of the data and potentially higher mass systems to look at with 01 data that's in the can. 01 has ended. Here we are in February. Here's going forward 2 years. We're going to spend the next several months commissioning the detectors to make them more sensitive. 01 was not at design sensitivity. We have a factor of 3 to go in range. It was a factor of 3 better than anything that had been done before, but it is not at design sensitivity. So the next few months will be to improve the range. Now, on this plot's actually volume. Volume is actually the more relevant thing, so range cubed. But once we get to hopefully 02, sometime in the late summer, we'll run for 6 months with hopefully a 3 times increase in volume. We'll take data opportunistically before then if we can, and again, afterwards.
Is Virgo going to be available?
Virgo is expected to be coming online somewhere in here. They've actually had some problems with some of their hardware. So the start date's a little uncertain, but they are working hard. When we get to 03, late in 2017, we'll have hopefully 10 times the volume. What this is going to mean in terms of rates is 02 could be able to see VVH detection once per month. 03 should be able to see one once per week. So hopefully that's what we have to look forward to. And before I close, I just want to say, here's the current local LIGO team. You should know that LIGO, I've only been here for a little while, as you all know, but Penn State has a huge history of LIGO, so we happen to be just a small group now, but over the years it's been an enormous team that's been here. If you see these folks around, buy them coffee, buy them a beer. They all worked very hard this fall. Probably I should be in violation of some human labor laws. That's all I have. Thank you.
So this signal was stronger than you expected. In previous incarnations of LIGO, would you have been sensitive to that signal? And going back over the previous runs, can you put any limits on? This
signal was almost right at the cusp of what would have been detectable before. So we observed, so another way of saying that is in initial LIGO, if you took this signal and translated it back to then, it would have been SNR 6. We would have not seen that above our background. But what it does mean is that we were really close. We were right on the verge. And this is, by the way, completely consistent with models that people have had. I mean, there were people knocking at our door in 2010 saying, why haven't you seen black hole mergers yet? And I'm not saying that their exact models were right, but in the spirit of what they were saying, it turned out to be right.
So any stronger signals are unlikely now because you would have seen them in previous runs.
Yeah, but I mean, to only a certain extent. I mean, we only
Right.
observe the design sensitivity for a finite amount of time. So, yeah. You can work out the statistics. This is not that uncertain. I'll let you manage the question.
Dog and then Grant. Under what circumstances would you get the best pointing?
Well, so we certainly need to have 3 detectors. And having detectors.
Just 2 detectors on.
Oh, with just 2 detectors? That's a good question. I don't remember exactly what location of the sky it is. I mean, basically, like, the thing is that, like, with 2 detectors, if you think of it just completely naively, like, you're sort of constraining yourself to a ring. Because, like, you imagine that the gravitational waves arriving at the 2 sites, the only thing that we really measure is the time delay. And that's because the gravitational wave detectors are fairly omnidirectional. Now, they're not exactly omnidirectional, so adding the amplitude and phase and polarization information, even though we don't have much, does break the sort of ring into a semi-ring on the sky. But in general, it's still mostly a ring. We're certainly most likely to detect things with LIGO that's sort of directly overhead or below the plane of the 2 detectors, just for other reasons.
Right.
So back to the spin. So you said they were either spin up or spin down, both not spinning. Would you call that like a degeneracy in your model? And if so, are there other degeneracies you have to consider when you like are doing this?
Yes, and tons. Yeah, that effective spin parameter is actually an attempt to come up with a single thing that recognizes the degeneracy there. So yeah, absolutely. The whole thing is, it has to be done with an enormous Monte Carlo. Everything is degenerate. Like seeing any one-dimensional PDF is being marginalized down from 15-dimensional space where like everything's square.
So a lot of this talk was on compact object coalescence, but what about the other searches, like the pulsar searches, the stochastic background, or the supernovae burst searches? Are those expected to be detecting things when you get into like O3 or O2? Or?
So that's good. I felt like I could finally get away from the standard LIGO talk where I give like the laundry list of everything, but no, it's a good question. Yeah, I don't know, maybe. Those other things are hard in the sense that, okay, supernova, if we get one close by, it has to be really close, but if we get one close by, there's a good chance we'll see something. The pulsar searches, I think the all-sky searches are maybe the most promising to find pulsars that are really close by that we just don't know about, but they're basically impossible computationally, so we only just poke away slowly at them. There are a lot of people doing some good work on sort of directed pulsar searches where we still don't know the full parameters, but we can forward sky positioning and other things. I don't really have a sense of whether or not they'll pan out or not, but everyone's still working hard on it.
I have 2 questions. What kind of environment do you expect to see such black hole icons? The second question is, do you expect to detect like neutron star binary very soon? Do they have like similar rates and then the sensitivity?
Yeah, so, okay, 2 excellent questions. First one, well, so the sort of possible hypothesis put forward as to how this could happen is normal binary stellar evolution, so in galaxies, but with low metallicity so that you could not only make big stars, but keep the mass around long enough to collapse into a big black hole. There are other scenarios that are possible, like capture scenarios and globular clusters and all of that. I think in most of those cases, you might not expect such equal mass. Like if the idea is that you're building up black holes from smaller black holes or other compact objects, the fact that you would have managed to do that twice and get the same equal mass seems unlikely. So this seems to me to probably suggest normal sort of stellar evolution, but slightly different than we thought before. As for neutron stars, the rates on those in principle haven't changed, though I've asked people who really like devote this sort of thing, devote their lives to understanding rates, what this implies about the other compact objects. And they said, well, it probably does, but we don't know yet. And so I'd be surprised if someone hasn't already put that paper on the archive. It's an obvious thing to try to see, under what assumptions does this imply changes to other objects. I don't personally know of any offhand. We still, even in the most pessimistic scenario, hope to observe at least one neutron star merger in the coming years.
So just to get back to the laundry list, I saw in one of the data tables that they think that this was a very loud burst and that it was face on towards us. Can you talk a little bit about how well we've determined the orientation of the orbital plane with respect to Earth?
That is in the parameter estimation paper. I almost included that plot. It's a bimodal, the inclination is a bimodal distribution, and it's correlated a lot with distance, as you might imagine, because the amplitude that you detect depends on the orientation. I think the answer is, it depends on how you look at it. I mean, if you look at the entire width of the PDF where there's support, it's like, you know, all of the angles, but it is sort of bimodal, so I don't know. I could show you the paper afterwards. You could determine what you think.
Okay. Final question.
I have a question when we all arrived from my ignorance about the general but so what you showed is that what you saw is consistent with like two compact optic orbit turn DR and that's what you're able to fit everything in here and you know the idea is supposed to be a black hole. Now my question is how sure are you that they are necessarily two black holes that you're seeing? You know, because I could imagine that maybe they are, you know, the masses are not like compact masses but they're like spread out or some of the reason why we see that. So,
That's an excellent question. So there's a lot of good reason to believe these are black holes, and if they're not black holes, there's something that we don't even know what that is yet. So the reason why they can't be a more extended object is because not only these objects have to be compact, but to get close enough together and be orbiting at the frequencies that would generate gravitational waves that we can detect, they have to be like hundreds of kilometers apart. If these were extended objects, they would have, you know, interacted hundreds of millions or billions of years ago. So they can't be white dwarfs even. Even white dwarfs are not compact enough. Not that you have white dwarfs that are this massive, but I mean like they have to be basically extremely compact to the point where the only sensible explanation is a black hole. Yeah, I'll leave it there. There's actually a little bit of an argument about why is this a black hole in the PRL. The people who wrote that argument are actually, I don't know if it'll happen, but they might try to put up like a physics today kind of pedagogical thing that goes through all the simple arguments. It's actually quite nice, but it's not great.
Yeah, you can follow question, conference, and after that, and just thank you again.